Welcome to this explainer on wireline operations. So here's the situation. After an offshore oil well is drilled and completed, it might just sit there and produce for years without any intervention at all. But eventually, something is going to need to be done inside that well. Maybe a safety valve needs testing, a downhole gauge needs replacing, a plug needs to be set, or a completely new zone needs to be perforated. Today, we're diving straight into the extreme engineering of well maintenance to see exactly how offshore crews pull this off. Which brings us to a really massive engineering challenge. See, an active well is basically a giant sealed pressure vessel. You have to somehow open it up, drop your tools inside, do some highly delicate maintenance, and then pull those tools back out, all while fighting back forces that want to violently erupt right to the surface. So the big question is, how do you actually put tools into a well that's sitting under thousands of psi of pressure without causing a blowout? Well, the answer for a lot of these operations is wireline. Wireline is really the hero of our story today. It's this incredibly ingenious mechanical solution that acts as a sort of minimally invasive surgical lifeline for a live well. So instead of pulling up thousands of feet of heavy production tubing using a giant rig, crews just use a thin steel cable, literally the wire, to lower specialized tools straight into that highly dangerous pressurized wellbore. To really grasp how wild this is, we have to respect the invisible enemy we're dealing with here, and that's pressure. If you've got a well extending down, say, 12,000 feet, the reservoir pressure down there can easily be hitting around 4,000 psi. To put that into perspective, that is more than enough force to blast any tool you try to insert right back out of the hole like a missile. You definitely can't just open a valve and drop something in. It has to be physically forced down.
So, how exactly do we beat that kind of pressure? We do it by building what's essentially a vertical space station airlock. First, the crew assembles the tool string inside a containment tube, which is called a lubricator. Second, they seal it up and pressurize that lubricator to perfectly match the well's internal pressure. Third, they open the Christmas tree valve, and finally, the tool is lowered into the well. Because the pressure is totally equalized, the well never actually breaches to the outside atmosphere. Pretty brilliant, right?
Let's break down how this airlock is actually built on the surface. Walking top down, we start with the lubricator riser, where the tools are waiting. Right below that is the wireline valve, which you probably know as the blowout preventer, or BOP. This is absolutely crucial. It's your ultimate safety seal. If things go sideways, hydraulic rams just slam shut around the wire to seal off the well. Up at the top, you've got a stuffing box or grease injection head to seal the moving wire, a tool trap to catch the tools just in case the wire snaps, and a chemical injection sub to pump in stuff like methanol to prevent icing.
Now, all of this heavy-duty surface equipment bolts directly onto the swab valve, right at the very top of the Christmas tree. It stands completely vertical right there on the platform floor, forming this seamless, high-pressure extension of the well itself. It's quite a sight.
Okay, so the choice of the wire itself is totally critical here. For most of your standard mechanical jobs, think setting plugs or clearing out wax, crews use what's called slickline. It's just a simple, single-strand piece of piano wire. But if you need live data, you're going to use an electric line. This one is a thicker, braided wire that transmits actual electrical signals. It allows the engineers to run really sophisticated logging tools or even lower live video cameras deep into the well to visually spot leaks. But using an electric line introduces a whole new headache. Because it's a braided cable, high-pressure gas can easily squeeze out through the tiny little grooves between those metal strands. To stop that from happening, engineers use a high-pressure grease tube. They actively pump this highly viscous grease into the injection head at 500 psi above the well's gas pressure. That literal wall of pressurized grease is the only thing lubricating the wire and keeping that lethal gas safely trapped inside where it belongs. All right, let's talk about the tools that are actually going downhole. I kind of like to think of the tool string as this highly specialized rescue team descending into the dark. You've got the rope socket that securely holds the wire. You've got your sinker bars, the jars, a knuckle joint to give it some flexibility, and then whatever specific running or pulling tools are required for that day's job. Every single piece plays a critical, specialized role in surviving the depths. Remember that 4,000 psi of pressure pushing up that we talked about earlier? Well, gravity alone is definitely not enough to pull a tool down into a high-pressure well like that. And that is exactly where the sinker bars come in. These are essentially just heavy, solid steel weights. They provide the necessary physical mass required to actually pull the wireline down against that immense hydrostatic pressure that's constantly trying to spit it back out to the surface.
And sometimes you need even more mass to really deliver a punch. If a tool needs to aggressively latch onto a stubborn safety valve or maybe pull out a jammed plug. The crew can add supplementary weights of up to 33 pounds to the tool string. Adding this extra weight specifically increases the kinetic effectiveness of our next tool on the string. And that tool is the jars. Look, if your equipment gets stuck thousands of feet down inside a pipe, you obviously can't just send a guy down there with a wrench to loosen it. So jars act as these remote mechanical downhole hammers. By pulling up or dropping the wireline from the surface, the jars deliver sudden, massive upward or downward impact forces. It's basically a remote-controlled hammer to break that stuck equipment free. Okay, so we've covered how to fix the well, but let's pivot for a second to one of the absolutely most critical and dramatic wireline operations of all. Think about this. After a well is drilled, it's lined with thick steel casing and surrounded by solid cement to keep everything structurally sound, right? But wait a minute. If the well is totally sealed off by steel and rock, how do you actually get the oil and gas to flow into the pipe in the first place? Well, the pay zone, which is the reservoir actually holding the hydrocarbons, is completely blocked off by those layers of steel and cement. To finally unleash the oil, a highly specialized wireline tool has to be sent all the way down to punch very precise holes right through that barrier and directly into the rock formation. And you don't drill those holes, you blast them. The wireline lowers a perforating gun that's fully loaded with shaped explosive charges. When they're detonated remotely, these charges fire high-velocity jets of energy that blast right through the steel casing, push through the cement, and go deep into the reservoir rock. This creates the exact flow tunnels needed for the oil to finally escape into the wellbore. The precision engineering behind that blast is pretty staggering. I mean, it's not just random explosions down there. The perforation design, things like the shot density, which is the number of holes per foot of casing, the angular phasing, and the charge size, all of that significantly affects the well's eventual productivity. Modern perforation design actually uses highly advanced computational models to optimize that exact perforation pattern for the specific reservoir and completion design. Now, once the well is flowing, pressure surveys become a key reservoir management tool. Wireline is used to essentially take the reservoir's pulse. Crews use the electric line to run a precision memory gauge down to defined depths in the well, continuously recording the pressure and temperature. By comparing those measured pressures to the expected reservoir pressure at those depths, engineers can calculate the true reservoir pressure, identify fluid contacts, like the exact boundary between oil and water or gas and oil, and assess the overall depletion. These surveys give us two distinct sets of data that build a clear picture of the reservoir's behavior. We have flowing surveys, taken while the well is actively producing, and static surveys, taken when the well is completely shut in. Comparing the two provides vital data on the well's true flow potential and helps diagnose skin damage, which is basically damage to the reservoir right near the wellbore that ends up restricting the flow of those precious hydrocarbons. But hey, what happens if the well isn't just vertical and instead drills horizontally for literally miles? Gravity sure can't pull those sinker bars sideways. Enter the Wireline tractor. This is a robotic downhole tractor equipped with electrical AC motors. Those motors drive hydraulic wheels right against the side of the casing, physically pulling the wireline tools horizontally to their destination. It's basically a robot defying gravity deep underground. Ultimately, wireline permits mechanical devices to be installed or removed in the production tubing with minimal interruption to the production process. It is the ultimate surgical lifeline. It lets offshore engineers maintain, diagnose, and repair massive energy infrastructure from the inside out, keeping global energy flowing smoothly with practically zero downtime. The sheer scale and precision of what happens invisibly below the ocean floor is just staggering. I mean, from balancing 4,000 psi with nothing but pressurized grease to driving robotic tractors miles horizontally underground, it really leaves you wondering what other immense, invisible forces of nature are being safely managed by offshore engineers every single day just to keep our modern world powered. Definitely something to think about the next time you flip a light switch. Thanks for joining me on this explainer, and as always, keep staying curious.